So this is just another statement of the general problem of which covers online advertising, content of web pages and search, and we have users, we have the context, which is the overall environment, and we have the inventory, the set of items that we could display, or in the case of say Amazon, we could recommend that people buy. And we have these complicated metrics with which to optimize, which at the simplest are total clicks, but really should be total revenue. And that revenue has to be total, integrated over lifetime. Remember, Netflix wants member retention, not members downloading movies today and then stopping. These are the issues that are brought together in these recommender systems, these different items which are involved, which include media, movies, articles. We have advertisements, we have the users, and so on. We have the context, which are maybe whether we're coming from a mobile or a desktop, the value of social media, and maybe query keywords defining the area we're working in. Then we've discussed quite a lot the non-trivial metric to optimize. Then we have the item pool. In query, we're searching all web pages. Maybe we only have 40 top stories, and we just have to choose the best 4, and so on. And sometimes we have manual intervention, editorial selected material, such as in some web news sites, and the other times we have anything. That's in some sense I actually do not know whether Google News has any editorial intervention to make certain you always get the top stories, because they say in the past they miss sometimes the top stories. I do not know whether the fact that I've never seen them miss top stories means that they've improved the algorithm, or whether the editorial insists that you cannot miss the top stories. And we need to get an appropriate diversity and also timeliness. Namely, we don't want to keep showing the same old things to people. We need to give them new things if they don't like the old things. We came across those ideas when we discussed Netflix. In terms of the context, we have both pull and push, as it says here. Pull is an example where the user types in a query. So that user's pulling something from the web. Push is something which the web is pushing at the user based on what the web knows about the user, the session they're in, the page they're at, the history, and so on. We have feedback on what the decisions made. You can get an immediate feedback by whether the user actually acts on what you do. If I go to that Yahoo page and then immediately go to CNN or something, then Yahoo is very unhappy. Then that feedback is either immediate or it could be actually later, might come from a later analysis. And the actual volume of data can vary from small numbers like 100,000 per day to many hundreds of millions per day. And then we also have various business models which constrain us, such as these so-called diversity rules, the editorial voice. Some websites are notorious for being a little more favorable to certain political points of view than others, and so on. All right, so we need to do these things quickly, like in the user item interaction. That's the click-through. And of course, as this amount of things to learn and discuss and use grows, but actually partly that's good because I pointed out earlier, the fact that we have so much data is precisely why we can do a good job on recommenders. I think Netflix had 4 million ratings per day. It's those 4 million ratings are driving the recommender engines. And if it had only 4 ratings per day, it would not be able to do any recommendations. So the scale of the recommendations is actually critical. And in some sense, remember the rule we had from the VP from Walmart, the more data, the better. So I actually think this is good, not bad, that the amount of data is increasing. We're going to get better results, and we're not going to increase the compute time, because as long as the compute time is linear in the amount of data, it's not going to give us trouble. The problems which give us trouble are where the dependence on system size is more than linear. Sparseness is an important problem we'll discuss a little later on. Namely, if you have all these users and all these items, any one user is only going to know about a subset of those items, a very, in fact, small fraction of those items, which means the overlap, direct overlap between any two users is usually very small. And that's an important constraint on models that work well. So here we point out in this first bullet about communities, and we already saw that in this lecture when we were discussing aggregating stores together. We need to decide what are good groups, and of course people, like everything in this field, most of it can be automated. You can find groups automatically. You can link people by their social networking connectivity. You can link people by their common buying habits and so on. So communities, which used to be relatively non-trivial to identify, such as users in San Francisco were easy for anybody to invent. And indeed, you can find, I know, users interested in baseball aren't too difficult to find. Just see who goes to baseball sites. But there are many hidden groups which can be identified with modern technology. And you need to find the right size group. If it's too big, you've averaged over everything and lost the specificity, which will help you give good predictions. If it's too small, there's too much noise. We also pointed out the web is so big and so dynamic and so online the whole time. We can do these A/B tests, which allow us to take any new algorithm and identify multiple collections of users and test it across a diverse set of examples. So this again describes the interaction between the various components. We have all these features of our recommender engines: information retrieval, clustering, taxonomies, those are categorizations, profiles, clicks, what the people are doing, social networking stuff, these communities. Then we have offline analysis. I mentioned that some algorithms actually take a long time, and you will run those algorithms. They can provide a base classification and organization, which then can be updated dynamically, because updates are usually much quicker than running an offline ab initio classification. And if you have a lot of data, you can classify it in a long offline job. Could take days to run, preferably just overnight, and then you can use it during the day interactively by just updating users by seeing how they fit into this classification determined in the offline fashion. So that's offline and online, because the basic online response has to be less than a second. And you need to take many methods and interact with them. And you need to do sampling, because you have so much data you can't look at all of it. We will come and look at this slide in more detail in the following slides. It just takes the Yahoo homepage and shows how it's optimized to decide how to take the various components and choose what to put there. Here's this example I mentioned before, that we have trade-off between click-through rate and value of those clicks. So if we measure utility per click in some fashion, which is to do with the amount of money the user spends or the amount of further exploration they do of the advertisements on the things they click through to, then it's certainly possible that one article could have a high click-through rate because it's a pretty exciting article, but has less utility than another article because it somehow maybe if it's too interesting in the first article, people don't look at the adverts. Or maybe the adverts don't match the article so well as the second article. So the click-through rate needs to be balanced with the so-called utility per click, and it's the product that basically is what you're trying to optimize. And obviously, it's fine to lose a bit of click-through if you gain in utility.